Welcome back. In this lesson, we're going to take a look at the skills we've been using over the last couple lessons on modeling sinusoidal functions to see if we can model some real life data. So most of the questions here I've pulled off of internet data to see if we can basically use real information to find something. So this first one here is actually a graph showing the average monthly temperature in Sudbury, Ontario. And you'll see that the x-axis, which isn't very convenient for us, but again, I pulled this from online data, it labels the axis as JFMAM, which is not numerical. However, those, because I'm really good at tricks here, is it's just the months of the year, January, February, March, April, May, it's so on. So what we're going to do so that we can actually have a numerical representation here is we'll let January represent month 1, February represent month 2, and so on, and then we'll go from there. So even though the graph shows letters, we're going to pretend they're numbers from 1 to 12. So below that, I've taken the data from that graph and I've read it off to the best of my abilities, and it's given me these numbers here. And what I'd like to be able to do is take those numbers and come up with something in Desmos. And I'm going to point out that I don't actually need to use Desmos for this, but I'm going to be using Desmos because it helps me visualize my thinking and understand what I'm doing better. Also, it lets me see if there's any kind of weirdness or funny things going on. And in many of these, there actually is some funny stuff going on. So what I'm going to do is switch over to Desmos, and I'm going to make a table, and it's going to use the values that are there. So let me switch now. Let me try that again. Okay, hey, it worked finally. Okay, so just a reminder, in case you've forgotten, the way that you can make these tables in Desmos is to type in T-A-B-L-E, and as soon as you've typed the word table in, it should actually switch over to a table. And then what I'm going to do is I'm going to put in my values, and I'll try and do this kind of as quickly and efficiently as I can. I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then my y values I'm going to plug in as -7, -9, -7, 4, 10, 15, 17, 17, 14, 6, 1, and -3. Okay. And if I look over on my graph here, I'll see that I have a bunch of dots. And what I'm going to do is just change my axes a little wee bit so that, again, this is as nice to read as possible. So I know my x values go from basically 1 to 12. So I'm going to plug in, I don't know, -2 to 14, a little above, a little below. I'll switch on my projector mode, take off the grid lines, and I want my x's to go up by 1s. I'm also going to make sure I switch over to degrees since that's how I'm going to model. And then for my y values, I see I've got a minimum of -9 and a maximum of around 17. So I'm going to maybe go, I don't know, -12 up to 20-ish. Again, just a little above, little below, so I'm not missing anything. And it feels like it's going up by too much, just going up by 10s. So maybe I'll ask it to go up by 2s. And it does not like that. That just means that the distance between 0 and 10, it'll get too crowded if I try and go up by 2s. So I'll go up instead by 5s. That should be good enough. All right. My settings are all good. And there's the dots that I have, which should look pretty much like the graph that I had on my sheet. So what I want to do is model this with a sinusoidal function. So I'm going to start off by just typing in a generic sinusoidal function. I'll just do f at x equals cos, and I'm going to put double brackets on the x, and again, I think you'll see why shortly. I'm going to switch this to, you know what, I like a blue line, and I like red dots. Feels like targets, something to shoot for. Okay. So from there, what I want to do is modify my function a little bit so that I can come up with something reasonable. Now, I'm going to take some educated guesses to start off without even doing any real heavy calculations. Um, One of the things I know is that this is something that's probably repeating every year, every 12 months. So I'm going to just take a guess and say that this is going to be 360 divided by 12. I might be wrong, but we'll see what happens. I'll make it a little larger so you can see all the numbers. I also know that my maximum up here is approximately 17 and my minimum is -9, and I know that those are 26 apart, so I'm going to guess my amplitude's around 13. What else do I know? Oh, now this is where it gets a little weird. I've got two maximum values here for July and August at the same temperature. So what I'm going to say is that my maximum occurs at maybe 7.5. So I'm going to do x minus 7.5. Now I have to shift this up a bit. It's currently at a maximum of 13 and I want it to go up to 17. So I'm just going to add 4 to my graph at the end here. That's right, I'm going to try and get this so everything's clearly visible. Oh, sorry. That's why I needed to make sure this was clearly visible. I put the +4 in the bracket. I want it outside the bracket. Okay, that's much better. Okay, and now you'll see that I'm actually not too far off most of the red dots that I've got. It's not perfect, and the truth is that temperatures don't follow perfect sinusoidal patterns. There's all kinds of atmospheric stuff going on and daylight hours and residual temperature left over. So for instance, when winter ends, even though the sun is bright, we still are essentially have an ice cube laying on us from leftover ice and snow. And likewise, when summer ends, even though it's starting to get colder, there's still kind of all that heat sink in all the warm material that got heated up all summer. So it doesn't follow it exactly. What we can do then is try and play with this a little bit to see if we can better hit the points. But I know I'm going to have a hard time getting this exact. And one of the reasons I can tell is that these points here at x equals 4, 5, and 6, they're a little bit left of the blue line, but down here at 2 and 3, they're a little bit right of the blue line. So I don't think I can move it left and right and fix both of those because I'd have to move it left to fix the upper dots and right to fix the bottom dots. What I could do, even though I think it's probably not correct from a scientific point of view, is I could try to actually lower the period. Maybe it's closer to 11. And now I'm hitting all the dots down here on the bottom near the minimum, but I'm really missing the ones up a little further. They're not hitting nearly as nicely. I'm also going to note that because I assumed the maximum was 17, but it's actually 17 in both July and August, which means that in the middle, it might actually go up a little bit higher. So maybe it actually should be something more like, maybe my amplitude's actually 14, or maybe it's 13 and a half. And you'll notice I'm really just playing with the numbers a little bit to see if I can find something that better represents the curve. It seems a little low at the bottom there. It could go up a little at the top. So I'm just going to change this to, I don't know, 5. That's too much, so I'll change it to 4.5. All right, and in the end, I think that's probably about as good as I'm going to be able to get to matching the points. And you'll notice that no matter what I do, some of the points are going to be a little bit off. So at the level we're at now in high school, we're not going to worry about the fact that we're a little off. We're going to worry about our equation at least making some sort of sense. We know the amplitude's around 13-ish. We know that the period's 11 or 12. We know that the first peak is happening in July or August, so about 7.5 months in, or move it right, 7.5. And we know that we're shifting upwards around 4.5. And your equation might be a little bit different than mine. Maybe you hit a couple of points better than I did, and maybe you hit a couple of points worse than I did. but overall it's about equivalent. Again, I'm not going to worry about this when it comes to asking you questions on the test. I just want to see that your answers are reasonable and that they show some sort of understanding of the general modeling process. You're not going to get places or equations that hit every dot because there is more stuff going on than just a basic like guaranteed thing. If the annual temperature patterns actually followed an exact sinusoidal curve, we would have weather models, so we would know exactly what temperature it's going to be on any given day in any given year, going as far into the future as we wanted. But we know that's not true. So there's going to be some variations. We're never going to hit all the points exactly, and that's all right. All right, going back to our paper. We came up with a model. We did okay. I'm not going to bother writing it down on the paper because we wrote it down in Desmos, and you can copy it off of Desmos if you'd like to. But let's look at question 2. Shani is riding a bicycle and runs over a wad of gum. Ew. Shani gets off the bicycle to remove the gum, but apparently is too incompetent to do so. It sits on top of the tire. Unable to remove it, Shani begins to ride home. The bicycle's tire has a radius of 33. Assuming that the speed is constant and that the tire makes one full rotation every 20 seconds. So I'm going to go through and answer these questions, but I'm going to do them while I'm in Desmos, so I'm not going to come back and write them down. But the good news is you can copy them down while I'm working in Desmos. So here's what we're going to do. We're going to kind of set this up this way. I'm going to just open a new Desmos window. In many cases, I find it actually faster to do this than it is to clear and reset all the details later. But I'm going to make another table of values. So I type in table. And this time, what I want to do is just say basically what happens. So we know that the tire goes around every 20 seconds. And I think it's fair to say basically where the gum is every quarter of a rotation. So I'm going to go up by 5s. And the question does ask us to do 3 full rotations. So I'm going to do 5, 10, 15, 20, 25, 30, 25, 30, 35, 40, 45, 50, 55, and 60. Okay, now we're going to ask ourselves what happens to that gum. So at 0 seconds, it's at the top of the tire, and the top of the tire would be 2 radiuses above the ground because it's the full diameter of the tire. So the radius is 33, so at this 0 seconds, this should be at 66. By the way, before I continue the rest of my table, just so I can start to see things, I'm going to do that. I'm going to go over to here and make some changes. So again, I'm going to turn that on, turn off the grid lines. My X values, we're going from 0 to 60 seconds. So I'm going to actually go -10 up to 70. And it's not going to fit on if I put in 1s, but if I go up by 5s, will that fit? No, 5s doesn't even fit. 10s fits. Okay, so we've got that going up by 10s. And then the y-axis, I know that the height of the gum above the wheel or above the ground is going to be as low as 0 and as high as 66. So again, I'm just going to do -10 up to 80. Some number that seems to make sense. Oh crap, my mistake. I did the wrong one. I did the y values were in the X box. So sorry, we went -10 to 70. Y values, I'll go from -10 to 80. And I'll go up by 10s there, I think, as well. Okay, I think we're good. Oh, and switch to degrees, of course, since we're modeling in degrees. Okay, so now let's think about what happens as the tire goes around. After 5 seconds, a quarter of the rotation, it will go from the top of the tire to the middle of the tire. So basically in line with the axle. So it's going to be at 33 centimeters high. And then at 10 seconds, it's halfway through, it's going to be on the ground. and 3/4 goes back up to 33, and then back up to 66 because it's gone one complete rotation. And then it basically just repeats this pattern over and over again. 33, 0, 33, 66, 33, 0, 33, 66. And that's gone through 3 full rotations. Now at this point, I can use the dots as my target, or I can just kind of think about what the variables are going to be moving along. So I'm going to say, you know what, this time let's do our height at t function. We can change up the variables a little bit. We'll start off with the amplitude. We know the gum goes from 0 to 66. Its amplitude is 33. That's actually the radius of the tire. Again, I have OCD. I like choosing specific colors. Okay, what else do we know? Well, we know it's a cosine function. I'll do the double x, or double bracket around the x. I know the midpoint of the function is 33 above the ground, so I can put plus 33 over here. Oh, I got to change my x to a t because I said this was a height at t function. I also know that the pattern repeats itself every 20 seconds, so I can put 360 over 20. And, oh, there, actually we're good. I didn't have to do a left or right translation because we actually started off at a maximum at the peak. And there we go. I came up with a function that modeled all of those points. So that was pretty straightforward. So we determined the maximum minimum height of the gum above the ground for part A. We used Desmos to make a table. And then part C, we came up with an equation that models the height of the gum above the ground over time. That seemed reasonably simple. All right, again, I'm not going to go back to the page because we don't need to. You've got the page in front of you. I'm just going to start talking through the question. So question 3 says that the Bay of Fundy, for those of you who don't know the Bay of Fundy, here, you know what, I'm going to just do it. Bay of Fundy is this beautiful area in Canada. So it's basically this this little area here between Nova Scotia and New Brunswick, and it's got some of the greatest tides in the world, which if you take a look at some of these pictures here, you can see the tides coming in, and the tides cut the rock, which makes these flower pot rock features. And it's got some of the highest tides in the world. Oh, that last picture, one sec. There was a staircase there in this picture right there. I've been on that staircase. I went down and walked around here. That's pretty cool. But anyway, that's the Bay of Fundy in Canada. If you ever get a chance to visit, it's quite a cool tourist attraction. So what we're going to do is we'll open up Desmos and make a new graph. And we're told that the largest tidal range in the Bay of Fundy goes from 2 meters at low tide to 24 meters at high tide. And it takes 12 hours to complete one cycle. That's not actually quite true. It takes slightly less than that. But anyway, we'll pretend it's 12 hours. And high tide occurred at 6 a.m. today. So we're going to make a table. And we're going to do this over a 24-hour period, but we're not going to do every hour. We're told that it occurs every 12 hours. We get a cycle. So what I'm going to do is just say that my first tide appears at a maximum at 6 a.m. So at 6 a.m., my high tide occurs, and my high tide was 24 feet. Sorry, 24 meters. And actually at this point, I'm going to go over to my settings and already make the changes because I have all the info I need. Turn that on, turn that off. My X, I want to go throughout an entire day. So what I'm going to do is just say, let's say negative 4 hours up to 28 hours, a little bit above and below 0 to 24. I'm going to go up by, can I go up by 2-hour intervals? Okay, that works. My Y's, I know that the high tide is 24 and my low tide is 2, so I'm going to go from, I don't know, negative 4 up to 30. I guess. Sounds reasonable. And I'll go up by, I think twos is too much, but I can go up by fives. And I'll make sure that, again, I'm in degrees, because if I'm not in degrees, my graph will not work right. Okay, so there's where I am at 6 a.m. I'm up at maximum height of the water. And I know that I know that this is going to mean that the table's out of order, but that doesn't matter. It'll still plot the right points. I know that I'm going to have my next peak 12 hours later at 1800 hours, if you like military time. So that's basically 6 p.m. And it's going to be back at a maximum again, so it's going to have a max there. Well, that means that halfway in between, at noon, 12 o'clock, I'm going to have a height of 2, because that's my minimum height. And I think that's all I'm going to really worry about. I guess we could put down, if you wanted, at 24 at midnight. I would have a height back at 2 again. That's my next minimum. But you know what? I don't think I need that. Let's just take it off. Okay, so my function. Again, I'll use height at time, since I'm modeling the height of the tides over time. And I know that there's a maximum of 24 and a minimum of 2. Those are 22 meters apart. So from max to min is 22. Half of that will be 11. Now I really feel like I should be using blue since it's tidal water. Okay, cos double bracket. I know that it repeats every 12 hours, so inside the bracket I'm going to do 360 divided by 12. It's starting to look a little bit better, but still a little wonky. I know my first peak happens at 6, so I'm going to go t minus 6. And I know that this peak is currently at 11 and wants to go up to 24, so I'm going to add 13. Again, I gotta make sure my entire equation is visible on the screen. But there we go. I think, change these to red dots. I think I hit all my points. I have my maximum up here, I have my low tide over here, my next high tide over there. That seems to properly model the information that I'm given in the question. So that's part B, determine the possible function for the graph. We just did that. Now the next one is kind of interesting. It asks us at 8 a.m., how high is the water? Well, if I wanted to do this algebraically, I could just punch in t equals 8, work out the answer and find out. Or I can just say the x value is right there. So the height of the water is at 18.5 meters. Technically, it's my t value. It doesn't mind it for functions, but it doesn't like where I just say t equals a number down. At least I don't think it will. Yeah, it does not like that. So I'm just going to do the generic x to put that one in. But either way, the intersection between the curve and x equals 8, or the 8-hour time, tells me that the height of the water will be at 18.5. Now the next one's actually a little bit more interesting even than that, and it's that larger boats may get stuck if the depth of the water is less than 5 meters. So at which time will the boats need to be careful? So the depth of the water is the h, or the y value. So I'm going to put down y equals 5. And what you'll see is that there's a couple times through the day where the boats could get stuck because the water level is lower than 5 meters. And those times are here and here. So basically, now just to be careful here, because I have a lot of students that will say, well, it's any time between 10:55 and 1:44, but decimals are not the same thing as minutes. So this is just over 10.5 hours, so just after 10:30 in the morning until just before 1:30 in the afternoon. So between about 10:30 in the morning and 1:30 in the afternoon, they have to be careful. And then similarly in the evening, turn those off. In the evening, they're going to have to be careful between about 10:30 at night, and 25 would be a full 24-hour day, and then another 1.5 hours roughly So they have to be careful between 10:30 and 1:30 in the morning. Algebraically, you could solve that. It's just a little bit trickier. You got to do some inverse cosines, and you've got to find your multiple possible answers, like we did back with our ambiguous law and all that in the trig unit. So anyway, that's the answers to those questions. All right, moving on. Question number 4. A buoy bobs up and down. So a buoy is those things that they put out in the water, usually as a marker for position, so boats know where they are and know to avoid certain things. But they bob up and down because the water itself is going up and down. So the information that we're given for this question, and I'm just going to start a new Desmos graph again. You know what? I'll just use f at x this time, since the last several have been h at t anyway. We're told that the distance between the highest and lowest points is 1.5, and that it takes 6 seconds for the buoy to move from its highest point to its lowest point and back to the highest point again. Assume it starts at its highest point and determine a model that gives the height above the lowest point as a function of time. Okay, so this one we're going to kind of do backwards. We're going to come up with the equation, then we're going to see what it looks like when we graph it. So let's work with the information we're given. At its highest point, it's 1.5 meters above its lowest point. That means distance from max to min is 1.5, which means that the amplitude is going to be half of that, 0.75. We know that it takes 6 seconds to do this, so we're going to do 360 divided by 6, and we'll kind of note that we're in seconds. And and as soon as I wrote that, I realized we need to fix our graphs here. So with that one on, that one off, x, we're doing something every 6 seconds. I'll just do enough for a couple of cycles, so I'll go from -2 up to like 14. And I'll go every 1 if I can. And then my y values, because this is the height above the lowest point, it's going to go from 0 up to 1.5. And I'll go from, I don't know, -1 up to 2.5. And I'll go up every 0.5. And then I make sure I'm in degrees. And as soon as I switch to degrees, you'll notice the graph fixes itself and it looks much better than it did before. Okay, so far this looks pretty good. It says it's at its highest point at 0 seconds. It's repeating itself every 6 seconds. So 612, that's good. And everything I think is good except that we need to move the graph up a little bit. There's no D value here. We're not moving it side to side, but we do have to move it up 0.75, which happens to be the same as the amplitude, so that it goes from its maximum point, 1.5 meters above the lowest point, and its lowest point is 0 meters above the lowest point. So now we've got a graph, and I think this makes sense. It's repeating every 6 seconds. It goes up to a max of 1.5 and down to a minimum of 0, and it starts at 0. So that wasn't too bad. Okay, for question 5, there's a set of data that I got off the internet here from a astronomy website, and it says that the following data set shows, actually, you know what, I'm going to bring this down for a second so we can see it. Here's a very big table, and what it's showing is basically the percentage of illumination of the moon each night over a month. So this was for November 1st to 30th, 2019. This was a real data set. And so when you look up and see a full moon, you're going to see 100% of the light, and that apparently happened on November 12th. And when you go up and see none or very little light, that's called a new moon, and that looks like it happened on November 26th. So what we want to do is put this stuff into Desmos and see if we can come up with some targets to hit. If it's all the same to you, you can pause the video if you'd like to try this on your own, but I'm going to pause the video so that I can actually put in all this data without wasting your time. So if you want to pause, do it. Otherwise, I will see you back here in about 2 seconds and we'll continue from there. Okay, so like magic, I have a table in Desmos with all of the values that we had in our question, and I'm going to try and set up everything here. So first thing I'm going to do is go over to my settings again, contrast on, make sure I'm in degrees, turn off the minor grid lines. My X values are going from 1 to 30, so I'm going to go, I don't know, -5 up to 35. A little above, a little below. If I try to go up by ones, it does not like it, so I'm going to go up by fives every 5 days. My Y values, obviously the percentage brightness is going to go between 0 and 100, so I'm going to go -10 to 110. And I'll go up by tens. And when I'm done, I should get a graph that looks fairly reasonable. So there's my graph. For some reasons that are kind of complex that I don't really want to get into, you'll notice that the peak on this one, the maximum, is wider than the minimum. So this is not going to be one of those ones that we model perfectly because, again, it's real data, and it has to do with kind of the complex motion of the Earth and the Sun and the Moon all going around each other at the same time. But anyway, we'll do what we can to best model it, and let's see what we can do. So I'm going to call this B at t for brightness over time. And I know that it's going to be a cosine function with like that. And I'm just going to keep modifying it until I get something that kind of, like I said, best represents what it looks like after I switched to all the pretty colors. Okay, so some things that I'm going to note first of all. The minimum is 0, the maximum is 100, which means that I should probably go an amplitude of 50, and my vertical shift will be +50. I need to fix my period. My period here, it seems to be repeating itself every month, roughly. So I'm just going to, for the heck of it, try 360 over 30. And I'm going to notice that my first peak happens at November 12th. So I'm going to do -12. And that was pretty quick. And I've got something that almost matches it. Now you'll notice that it is a little bit off. I could try to do a couple things. First of all, the one thing on here that I did kind of take an estimate at is that it repeats every 30 days. I don't know that it does. It just happens to be a 30-day month. So I'm going to try maybe making that a little bit smaller since the distance between my max and min, sorry, that's the minimum. I actually want the real dot. I'm going to turn that off for a second. My data maximum is at 12. My data minimum is at 26. So they're actually only 14 apart. So I think this should probably be closer to 28 if they're 14 apart. Again, that doesn't perfectly hit stuff. I could try and play with it a little bit more, but I don't think I'm going to get a much better model than this. I'm sure about the 50 at the beginning. I'm sure about the 50 at the end. I'm sure about the 12. The 28 is the kind of the problem. So I could play around with it and see if there's a number that makes it a little bit better. And I'm not sure that there really is going to be one because, again, it's not technically exactly a perfect cosine function that we've got. So anyway, that's not a bad model right there to represent it. We got the peak in the right place. We got the minimum in the right place. We've got the period looks more or less correct. Maximum min values are about correct. Yeah, I think we're good. So that would be the function that I would come up with. Okay, now this last one here, and again, I'm going to just bring up this picture on the screen quickly. We want to see if we can determine a model that gives the number of employees given the year. So this particular thing says, here's the employees in thousands. And it goes from, well, this graph goes from 150 to 270, but the minimum actually looks like it's more like 210. And the maximum is more like 2, 260-ish, a little under 260 maybe. And we're going over time. Now this there's no reason this has to be sinusoidal except that it kind of looks like it. So let's see if we can come up with a model. So what I'm going to do is I'm going to just kind of read off numbers from the graph and make a table here. And this one I think we can do relatively quickly, so I'm not going to pause the video for it. But I will make my new Desmos graph. And you can try this with me if you'd like. So the years on our graph take us from 85 to 95. 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95. You, by the way, can do each point, like the whole point by itself. I find it easier just to fill in all the X's and then come back and fill in the Y's. So again, this is going to be a little bit of a guesstimate here because I'm just trying to read off of a graph that's not completely clear and has bad scaling on it. I'm going to say the first number is around 225, and then it goes up to around 240, and then it goes up to a maximum at about 260, and then comes back down a bit to, we'll say, 235. 89, it looks like it's around 225. Again, these are pretty rough estimates because the graph doesn't have a great scale. 210, 215, 225 again-ish. 93 is up to 240. 94 looks like it's around 255. And 95 looks like it's around 260. Okay, so again, a reminder that this is not actually meant to be sinusoidal. It just want to see if we can roughly approximate it. So we're going to have to make some compromises. We're not going to hit all the points by any means. But I know that my X values go from 85 to 95, so I'm actually going to go 83 to 97. Just to go above and below. I'll turn off the minor grid lines. I'll turn on the degrees. And that one. Okay, and my Y values, just looking at it, I'm down to a minimum of about 210 and up to about 260. So I'm going to go, let's say 200 to 270. So everything fits on. And I'm going to step by 10s, I think. Maybe 5s. I can fit 5s on there. Okay. So not by any means perfect, but that's roughly what my graph looks like. So what I'm going to do is take some rough estimates of what this should be. So this is, I'll just use generic f at x for this one. Cos double bracket x. I know the amplitude has to go from 210 to 260, so that's a 50 increase. So the amplitude's half of that, 25. And I know that the end value is either going to be the max minus 25 or the min plus 25. Either way, it's about 235. Plus 235. Oh, the period. I need to fix the period. It looks like my two maximums are at approximately 1987 and 95. Those are 8 years apart. So I'm going to put down 360 over 8. And the first peak occurs at 87, so I'm going to do x minus 87. Okay, and here's the question. Does that anywhere close to modeling the data accurately? And the answer is not particularly. Maybe if we tried to move it over a little bit here, change this to an 86. Our peaks miss, 86.5 maybe? 86.8, I don't know. Okay, so we're not going to hit this one at all perfectly because it's not meant to be. But as far as the max and mins go and the distances between them, I think that's actually not a horrible model. It's clearly not right, but again, real data often doesn't do this. So this isn't about getting the right answer. It's about understanding how to play with the variables to get it to do what you want it to do. And despite the fact that the numbers aren't nice, we were able um, to do something, to come up with some formula that best approximated what we saw as a sinusoidal function. All right, I'm going to stop there. And there are some practice problems here. Some of them are more precise than others. This one's fairly nice numbers. This one's pretty nice. You'll notice that it actually gives you the blue curve of best fit. The red X's are the actual real data. Here, the black dots, the black crosses are the real data, which is definitely not sinusoidal. It does some weird stuff in the middle, but the red is an approximation of it. So see if you can do that. And then this one's not too bad. And yeah, just try these few. So there are some equations at the bottom there if you've tried them. But again, try to do the best you can to model those. Use Desmos if you'd like, but try to understand where the numbers are at least coming from. All right, I'm going to stop there. Do your best on those questions. If you've got any problems, let me know and I will do my best to help you out. Otherwise, I will see you in the final lesson of the unit.